the forensic investigation into the loss of the Boeing B-17G Liberty Belle centers on two linked physical boundaries: a failed fuel containment repair in the left wing and the muddy ground that limited the firefighting response after landing. On June 13, 2011, a rapid in-flight emergency forced a severe operational trade-off. The primary objective was immediate emergency egress, while the secondary battle was post-landing fire suppression under field conditions that emergency crews could not quickly overcome. The sequence initiated during a standard flight. The aircraft departed Aurora Municipal Airport at 9:38 in the morning. The crew established their initial climb and proceeded along the planned routing. Within minutes after takeoff, the operational state of the flight fundamentally changed. The crew had already noticed a faint odor in the cockpit and a small amount of smoke near the radio room. About that time, the pilot of an accompanying T-6 Texan chase plane transmitted a direct radio call to the bomber crew. The chase pilot reported a visible, active fire on the left wing of the aircraft, and a third crew member on board the bomber then confirmed a fire behind engine number 2. This external visual confirmation turned an uncertain cockpit warning sign into an immediate fire emergency. The bomber crew faced a strict time limit. The pilot had to evaluate two distinct recovery paths. The first option involved attempting a high-risk return to the departure airport with an active, uncontained wing fire. Returning to the runway offered guaranteed access for heavy crash rescue equipment, but it critically extended the flight time under deteriorating structural conditions. The second option was executing an immediate off-airport emergency landing. This would place the aircraft on the ground faster, minimizing airborne exposure, but it carried the inherent risks of unprepared terrain. The pilot selected the immediate off-airport option. He initiated a descent toward a cornfield near Oswego, approximately 8 miles southeast of Aurora Municipal Airport. The crew configured the aircraft and executed a controlled, gear-down emergency landing. The aircraft rolled to a complete stop within the field, and all 7 occupants evacuated safely. Only one minor injury was reported during the rapid egress sequence. However, the local environment immediately imposed a hard physical limit on the next phase of the response. Once the aircraft was burning, the same agricultural setting became a severe access problem. The official record identified muddy field conditions as the access constraint that slowed heavy firefighting vehicles. Heavy municipal fire apparatus require a stable surface before crews can safely drive close to a burning aircraft. In this case, the muddy field conditions prevented the responding vehicles from getting close enough quickly enough to attack the fire at its source. Fire crews had to balance the urgency of suppression against the risk of bogging down heavy trucks near a burning bomber loaded with fuel. The result was a delay that allowed the fire to grow beyond the point where the airframe could be saved. The bomber remained isolated in the field as the fire moved past the airframe saving window. How does a controlled, survivable off-airport landing immediately transition into a near-total structural loss? The physical survival of the 4-engine bomber hinged entirely on a strict thermal limit. The uncontrolled fire established a hard boundary between the isolated components that would survive and the primary structure that would completely cease to exist. From that point, the initial flame front burned unchecked. Investigators needed to understand exactly how the thermal sequence initiated and why it caused such complete structural destruction. The physical mechanics started with a localized failure in the left-wing fuel system. In-flight photographs showed fire on the aft lower portion of the left wing between the inboard and outboard engines, and a crew member confirmed fire behind engine number 2. In the same region were fuel tanks feeding the left side engines, including the repaired number 1 main tank. Investigators could not determine the exact ignition source because of the fire damage. The safer conclusion is narrower but still powerful. Leaking fuel inside the open wing structure likely vaporized into a flammable mixture, and that vapor or liquid fuel likely encountered hot surfaces from nearby engine components, initiating the in-flight fire. Once the aircraft came to a complete stop in the field, the aerodynamic slipstream vanished, but the fuel leak continued to feed the localized fire. The static environment fundamentally altered the thermal dynamics. Without the relative wind to blow the heat rearward, the extreme temperatures radiated directly upward and inward into the wing root. This initiated the thermal destruction boundary. The primary construction of the aircraft relies heavily on a semi-monocoque aluminum alloy airframe. Aviation-grade aluminum provides an excellent strength-to-weight ratio necessary for flight, but it possesses a critical vulnerability to sustained high temperatures. When exposed to a sustained aviation fuel fire, aluminum skin and internal structural members can lose their load-bearing integrity long before the whole structure melts. The fire did not need to liquefy the entire bomber to make the central airframe unrecoverable. As it burned without rapid suppression, it consumed significant portions of the fuselage and the inboard sections of both wings, severely damaging the region around the repaired fuel tank and distorting the original geometry of the aircraft. Other materials within the fire zone reacted differently. Steel and dense alloy components such as engine blocks, heavy engine mounts, and specific internal system fasteners require significantly higher thermal loads to melt. These denser elements retained their basic physical shapes, although they suffered severe heat discoloration and surface damage. They dropped straight down into the molten aluminum puddle as their surrounding support structures vanished into the ash. The unsuppressed fire eventually exhausted its available local fuel supply before it could spread to the extreme extremities of the airframe. Because the central fuel tanks breached and burned out rapidly, the thermal progression finally halted. The extreme outboard wing sections and the aft tail unit remained structurally intact. These isolated sections stood as untouched islands above the massive burn footprint, disconnected from one another by the destroyed center section. This selective destruction created a profound forensic constraint for the investigation team. The specific physical zone where the mechanical failure initiated was located in the heat-damaged left wing fuel tank area. The critical hardware was no longer available as a clean, installed assembly that could simply be traced line by line, but it had not vanished into ash. Investigators still recovered and examined pieces of the number 1 fuel tank and the repair hardware associated with the leak. The standard procedures for examining aircraft systems, routing diagrams, and structural load paths were completely impossible to execute on a melted airframe. With the primary aluminum structure reduced to ash, how can investigators physically prove the origin of the mechanical failure? The maintenance logs presented a glaring physical contradiction for the investigating team. Records showed that a fuel leak in the number 1 main tank had been evaluated and repaired shortly before the accident flight. The key question was whether that repair had actually sealed the crack or merely covered a failure that was still progressing. The decisive evidence would have to come from controlled examination of the recovered repair hardware. The causality question therefore moved from wreckage reconstruction to the recovered number 1 fuel tank pieces and the repair area documented in the maintenance history. During post-accident examination, the tank was filled with a small amount of water, and droplets leaked from the aft repair area near bolt number 2 and the partially separated channel. The aluminum C channel was then removed, and the repaired region of the tank was saw-cut for closer microscope examination. This shifted the investigation from a broad wreckage survey to a targeted materials analysis of the exact fuel containment boundary that had failed. The critical hardware recovery was not a dense alloy artifact sifted from a slag pool. It was an aluminum C channel associated with the repair to the number 1 main fuel tank. After the accident, the channel was found partially disbonded from the welded tank flange. Its importance came from where it had been installed, where the leak appeared, and how it had separated, not from any special heavy alloy construction. The recovered repair hardware then moved the investigation from the field to the National Transportation Safety Board Materials Laboratory, where controlled examination could test whether the containment failure had preceded the fire. Extracting a suspected component from the ash is only the first step. What will microscopic analysis reveal about its failure mode? At the Materials Laboratory, engineers faced the delicate operational task of separating post-crash thermal damage from pre-impact mechanical signatures. The controlled environment gave them the conditions the muddy field could not. The materials team therefore treated each step as a controlled examination of the repair boundary. The recovered tank pieces and channel were documented as received. The repair region was leak tested, the channel was removed, and the repair area was cut from the tank for closer examination. Investigators then evaluated sealant adhesion, sealant chemistry, the weld seam, and the fracture surface using laboratory methods suited to each question. With the repair area prepared, investigators did not look for a failed weld inside the C-channel itself. They examined the welded seam of the fuel tank flange. Once sealant along the flange seam was removed, a longitudinal crack was visible along the center of the weld seam, about 7.2 inches long. The crack ran through the region of the repair bolts, including bolt numbers 2 and 3. For closer examination, the repaired tank section was cut open, the fracture surface of the weld bead crack was exposed, and scanning electron microscopy was conducted on that fracture surface. The microscopic examination yielded the critical physical signature. On the weld bead fracture surface, engineers observed striations consistent with fatigue crack propagation. That evidence indicated a progressive failure in the fuel tank seam, one that existed before the emergency landing and the post-landing fire. The heat damage complicated the examination, but it did not erase the fatigue features preserved on the fracture surface. This microscopic crack provided the structural proof of the fuel leak. The crack was in the welded seam of the number 1 main fuel tank, at the same repair area that had been sealed with bolts, sealant, and an aluminum C-channel. When that seam continued to fail, the repair could not maintain the fuel containment boundary. That loss of containment provided the fuel source for the left-wing fire already documented during climb out. The physical evidence chain was now completely locked, linking a microscopic maintenance flaw directly to the massive in-flight fire. Based entirely on this targeted metallurgical proof, the investigation reached a definitive structural conclusion. The National Transportation Safety Board officially determined that the probable cause of the accident was an inadequate maintenance repair on the fuel tank. The flawed weld failed under standard operational loads, establishing a continuous fuel leak that destroyed the aircraft. The disciplined forensic workflow successfully extracted a concrete mechanical verdict from an otherwise melted airframe. With the forensic investigation closed and the primary structure destroyed, what future remains for the surviving extremities of the aircraft? The official closure of the federal safety investigation forced an institutional decision regarding the physical remains of a B-17G accepted into Army Air Forces service in 1945. With the targeted metallurgical analysis complete, the remaining wreckage became a restoration and recovery problem rather than a causality problem. The operational objective at the location shifted. The mission was no longer focused on discovering why the fire had started. The new objective was the physical stabilization and retrieval of the surviving historical hardware. The recovery team faced a stark physical reality upon re-entering the agricultural field. The primary aluminum fuselage and the critical inboard load-bearing structures were entirely erased by the prolonged heat. The center of the aircraft was merely a compacted footprint of ash and slag. The surviving outboard panels and aft tail section now became the only large assemblies worth recovering. The Foundation had to decide whether to scrap the massive remnants or attempt a complex salvage operation. Because original 1940s bomber components are heavily restricted and irreplaceable, the Foundation elected to execute a full hardware extraction. The physical removal of the surviving sections still presented a severe handling challenge. The fire had consumed much of the aircraft, but the tail and outboard wing sections survived well enough to justify recovery. Those large assemblies had to be handled as historical aircraft structure, not scrap metal. They were fragile, heat-affected, and valuable both as restoration material and as proof of continuity for the rebuild. The recovery team therefore focused on transporting the surviving parts safely back to Douglas, Georgia, where the Foundation could decide what could be repaired, what could serve only as a pattern, and what would have to be replaced. The physical site was finally cleared, but the complex operational problem was just beginning. How does a Foundation resurrect a flying bomber when the core fuselage no longer exists? The operational timeline for heavy aircraft restoration operates on a scale of decades. When the Liberty Belle originally returned to the air in 2004, it represented a massive expenditure of engineering hours and financial capital. The loss of the primary structure in the field instantly erased that established operational status and completely reset the time window. As the transport convoy delivered the surviving aft fuselage and outboard wing panels to a specialized restoration hangar in Douglas, Georgia, the Foundation faced a unique mechanical challenge. They possessed a fully intact, historically verified tail section, but they lacked a complete aircraft to attach it to. The engineering team could not treat the rebuild as simple new construction, but the legal boundary was not an absolute ban on fabricated structure. Returning a vintage aircraft to airworthy condition depends on approved data, acceptable repair practices, inspection, records, and the aircraft's identification and registration history. Under FAA maintenance guidance, fabricated replacement parts can be acceptable when they provide an equivalent level of safety and are produced under methods acceptable to the administrator. For Liberty Belle, the practical strategy became a disciplined mix of salvage, donor assemblies, and newly fabricated pieces. By combining the surviving verified Liberty Belle structure with carefully documented donor and fabricated components, the foundation could preserve historical continuity while rebuilding the destroyed forward structure under airworthiness oversight. Executing this structural merger requires immense geometric precision. An aircraft fuselage is not simply a hollow tube. It is a stressed semi-monocoque shell designed to carry flight loads through skins, frames, bulkheads, stringers, and longerons. Any major repair to that structure has to preserve load paths, alignment, corrosion protection, and documented workmanship. Splicing donor assemblies together is therefore slow, highly methodical work. Mechanics cannot simply weld heavy aluminum fuselage sections into place and call the airframe restored. They must inspect the donor structure, remove corrosion, verify critical members, replace damaged skins and fittings, and rebuild the joints using acceptable aircraft practices. On Liberty Belle, the restoration team reported completely rebuilding the original outer wing panels, using donor inner wing panels, inspecting spar tubes for cracks and corrosion, rebuilding the forward fuselage with obtainable parts, and fabricating upper cockpit and fuselage sections as needed. The surviving tail section remains one of the vital physical anchors of the project. Much of the heavy structure in the tail could be reused, while heat-damaged or time-damaged material had to be cleaned, repaired, reskinned, or replaced. Each usable component preserves part of the aircraft's history. Each replacement component has to meet the mechanical standard required for a safe return to service. Rebuilding a heavy bomber through salvage, donor parts, and fabrication does not guarantee flight by itself. It creates the structure that must still pass inspection, systems work, documentation, and airworthiness review before the bomber can safely carry maximum loads again. The preservation of aviation heritage through physical reconstruction remains an ongoing, decades-long engineering problem.